Welcome to the CopperSpice YouTube channel, and thanks for joining us. In this video, we're going to talk about the wonderful world of templates. C++ templates in the real world. We're going to start with a brief overview about what templates are and when you should use them. In this video, we are going to show 3 real examples of templates which we have used in our open source work.
We have talked with several members of the C++ Standards Committee, and one of the most challenging tasks is naming things. The name template is a really good description for what this is. The idea behind a template is to provide source code with some of the details missing. The compiler will then be responsible for figuring out how to expand the template for each context and each time it is used. There are several different kinds of templates, and they have different rules. The first kind of template we're going to talk about is the class template, or templated class. A templated class is a class which does not specify some piece of information required to fully use it. This template must be instantiated at compile time, and when you use the template, you must supply enough information for the compiler to fill in the missing details. Each time the compiler inserts a new set of details into the class template, it creates a separate class. These template class instantiations have no relationship between each other. Once the compiler has finished filling in the missing details, all that remains is a normal class, exactly as if you had written a class yourself. At runtime, these classes may be instantiated, and you can create objects and destroy objects of this class as you would with any class. It is important to understand that new template instantiations cannot be made at runtime. Template instantiations only occur at compile time, and at runtime all that can be done is use the instantiations that were created by the compiler.
A function template is also instantiated at compile time. The compiler creates a new function for each data type used in the application or library you are compiling. The only data types which are used are those required or deduced in the calls to the template function.
A question that is not asked as often as it should be is, when should I use templates? When are they the right tool for the job? One of the most common places this comes up is deciding whether to use a templated function versus an overloaded function, or the same question about methods. The fundamental difference here is that generally you want to use a template when you want to do the same set of actions no matter what data types you're operating on. Whereas if you want to do a different action depending upon the data type you are passed, you probably want an overloaded method, not a templated method.
Our first example involves a templated class. QStringView is a new templated class in the CopperSpice library. It provides read-only access to part of a string. QString8 and QString16 are new string classes in the CopperSpice library. They support UTF-8 and UTF-16. The template parameter for QStringView must be a type of string. QStringView was designed to work with both QString8 and QString16. But since QStringView is a templated class, it can accept any string as long as the data type of that string meets certain requirements.
This is a portion of the code in CopperSpice that we added to define QStringView. One of the benefits of implementing QStringView as a template is that we didn't need to write QStringView8 and QStringView16 as 2 separate classes, with a great deal of code duplication. This also allows the versatility of using QStringView with classes that support different encodings. We are providing 2 using declarations in this file to make available QStringView8 and QStringView16. These are aliases for particular instantiations of QStringView. Since an instantiation of a class template acts exactly like a class, This means users can use QStringView 8 as if it were a class without having any idea that it is based on a template. In order to set up these using declarations, we need to first forward declare the templated class QStringView, as well as the classes that it will be instantiated with, QString8 and QString16. QStringView is based on a class in the CsString library called CsStringView. CsStringView is also a template, based on the type of string it is operating on. This means that our QStringView class template inherits from a templated parent and passes the template argument to the parent. This is a very common technique in designing a templated class. Before we discuss example 2, we'd like to briefly review the syntax for variadic templates and parameter packs. In order to declare a variadic template, you use the ellipsis operator. When it appears to the left of a declaration, it declares a parameter pack which can have any number of elements in it. When it appears to the right of an expression, it unpacks the parameter pack that appears in that expression into separate arguments. The convention for variadic templates is often to use t's as the parameter pack containing the data types and v's as the parameter pack containing values. These are two separate parameter packs and they have different meanings.
QStringParser is a new class we've added to the CopperSpice library. It provides functionality to parse an existing string. Prior to adding the QStringParser class, there were 8 different overloaded methods for arg. We changed the method name of arg to format args, since this is a more accurate name. Format args is a variadic template in QStringParser. For API compatibility, we also wanted to put a wrapper in the QString8 class.
In the QString8 header file, we had to have only a forward declaration of QStringParser to avoid a circular dependency. This presented an issue because we needed to call a method in QStringParser, but all we have available is a forward declaration. The solution to this involves deferring the call to the QStringParser format args until later in compilation when all of the classes are available. We discovered that we could do this by setting up a separate template parameter which was defaulted to QStringParser. The user could, in theory, override this to select a different string parser. This means that the compiler may not resolve the call to format args until this method is actually called. This is a useful technique for avoiding circular dependencies in templates, because often a forward declaration is not sufficient. Since the format args method in QStringParser takes a string followed by any number of args, all we have to do in QString is forward ourself as the first parameter and all of the arguments we received as the subsequent parameters. In the QStringParser header file, we declare that format args method as a variadic templated function as well. It receives a string as the first parameter and any number of arguments, applies the arguments to the string, and returns a new string of the same type. Not only have we reduced the number of methods required to accomplish this task, but we have also removed any limitations on the number of arguments that can be passed to format args. This variadic templated function also points out a different idiom for developing variadic templates. All this function does is take the data that it has passed, place it in a container, and pass it to another method, multi-arg. Multi-arg is a private method in QStringParser. Importantly, multi-arg is not a template. It simply takes a QVector containing all the arguments. This means that there is only one version of multi-arg. It is not instantiated multiple times as you use different numbers of parameters for the format args method. Another topic that comes up with templates is the use of sFine, and we'd like to touch on this briefly before we continue. sFine is an acronym for Substitution Failure is Not an Error. This is a description of the rule in C++ that when a compiler is instantiating a template and it encounters an error while expanding the template declaration, it is required to throw out that template declaration and see if another one may work. Sfine isn't actually something you define in your templated class. Sfine is just a rule that you can make use of when you set up your templates. This allows you to have one template thrown out, and if there is another template that possibly matches those arguments, it will be used and no error will be generated.
As we begin example 3, we need to show the relationships between a few classes. CsString is the base class, which takes an encoding like UTF-8 or UTF-16 as the template parameter. It provides an API similar to stdstring. QString8 exists to provide a replacement for the QString class, which did not support Unicode. Adding support for QString16 or any other coding is now trivial. QStringView 8 can be treated as a class, even though it is really a specific instantiation of the templated class QStringView. This is done by the using statement. One of the methods we wanted to add in CopperSpice was a constructor in QString8 that takes a QStringView8. The code in the QString8 header file is pretty straightforward. It simply calls the parent constructor. We expected it to call the code in the CsString header file, but we received a compiler error saying there was no matching function. So let's take a step back and figure out why this does not match and if there's anything we can do.
So let's look at these class relationships again, but let's fill in all of the information that will be specified once the compiler has finished instantiating templates and resolving all of the template parameters. Note that there are no template argument lists left. Everything has been fully resolved. QString8 inherits from CsString UTF-8, and QStringView8 inherits from CsStringView QString8. If instead of using a QStringView8, we wanted to construct a QString8 from a CsString UTF-8, there would be no issue, because there is a copy constructor in CsString which matches. The template type parameter used for CsString is UTF-8, and CsString knows exactly what this is because it was instantiated with a template parameter of UTF-8. This matches perfectly.
So why is passing a QStringView8 to the CsString constructor not allowed? Well, the CsString constructor wants a string type of CsString with a template parameter E, where the E is a UTF-8 after template resolution. The compiler is simply not allowed to substitute CsString UTF-8 for QString8, even though there is an inheritance relationship. So the inheritance relationship is actually causing a type mismatch, and the compiler is unable to resolve this. What we need to do is relax the conditions so there is a match. The way you do this is by changing the method to a templated method. We want to be careful because we don't want every string type to be allowed. So the solution is to define a compile time test for this templated constructor in CsString for only the things we want to match.
Since we don't want the compiler to look at the inheritance relationship, instead we set up some code so that the compiler will look at the data type contained inside the string view. We will do this using some type traits and mechanisms that were added in C++11. The first thing we need is enable if. Enable if is a mechanism that generates either a data type, in this case void since we didn't override it, or a compile error if the value is not true. The argument to enable if is asking a question. Is convertible is a type trait that asks if A can be converted to B, and the : value at the end is how we get the Boolean result back and feed it into enable if. The first argument to isConvertible is the data type that we really are curious about. And this is a decal type that says, if I were to do this, what type would it yield? And what we're looking for is for it to yield something which can be successfully converted to CsChar. Inside the decal type, we need to put an expression that gives us what we want to know. The first thing we do is dereference, because we really want to dereference an iterator from the view and find out what it will return. In this context, we don't have an iterator available, which means we can use a mechanism in the standard called decalval to create one. Decalval says, I would like you to generate a fake u::const iterator so that I can try dereferencing it and then feed that information to decal type. The end result is that this constructor will be available if and only if the data type that you get when you dereference a const iterator from u is convertible to CsChar. Once you understand the syntax that's used for decal types and type traits and things like enable if, code like this is actually not that complex to write. What can be challenging is figuring out what the correct condition is that you need to express. If you want to know more about type traits, there are many other classes similar to isConvertible that are available in the standard.
For more template examples, take a look at the CopperSpice CS core library on GitHub. You will see these examples in the source core string folder.
For more information about CopperSpice, please visit our website at www.copperspice.com.
Thanks for watching our video, and we hope you found the content of value. If you have any questions, please feel free to email us or leave us a message on our CopperSpice form. We do enjoy hearing back from you.
Please make sure you subscribe to our YouTube channel and come back in 2 weeks for our next video.